Hello, my name is Tim Davies and welcome to our FTS online class. So we're now on to the last reading of quants. Isn't that fantastic? It's nearly over. And the reading we're going to be covering is linear regression. So the good thing about this reading is that it's nice and short. So I don't foresee any problems here. So let's get started. Right, so we're going to start off with simple linear regression, and with simple linear regression, we get the dependent variable and the independent variable. So let's start with the dependent variable, which is also called the explained or the y variable, because we find it here on the y or the vertical axis. So this is the variable whose variability the regression model tries to explain. So we're going to use the return on stock A as our dependent variable. So in other words, the model is going to try and explain the variability of the returns on stock A. And then we've got the independent variable, which is also called the X variable, because we find it here on the X or the horizontal axis. Now, this is the variable whose variation explains the variation of our dependent variable. And we're going to use the return on the market as our independent variable. So in the US, they usually use the S&P 500 as a proxy for the market. And remember what the S&P 500 is? We discussed it some time ago. The S&P 500, that is just an index of the 500 biggest stocks in the US. So we use that normally as a proxy for the market. So what we're doing then in our model or our example is that the return on the market, that is going to explain the variation of our dependent variable, and our dependent variable being the return on stock A. So the return on the market, that is going to explain the variation of the returns on stock A. Good. So just before we go on to the next point here, I want us to take a look at the scatter plot down the bottom here. And you can just ignore this red line I've drawn in over here for now. We'll come back to that red line in a few minutes' time. But remember scatter plots, which we did way back when? What do scatter plots do? The scatter plot shows us the relationship between two variables. So in this scatter plot, we're looking at the relationship between the return on the market and the return on stock A. And I've got the data for the scatter plot over here on the from this information over here on the bottom left of the slide. So let's see what we've got in this information. We've got here the monthly returns on the market, and we compare the monthly returns on the market down this column here to the monthly returns on stock A. So remember the market return, this is our independent variable or our X variable. So let's put an X over there for that column. And then stock A, that is our dependent variable or our Y variable. So let's put a Y down this column for stock A. So what we can do then in each and every month is compare, how did the market return do compared to how did stock A do. So what I want to do is take a look at August, and why I'm using August, it'll become clear in a few minutes time. We're going to be picking on August in quite a big way as we go through this class. So in August, the market did 2.5%. So that's over here. The market did 2.5% there. And stock A, it did 2%. So we're going to put in 2% there. So this dot over here, this is the dot that is representing August. So of course, we've got 12 months, and then this means we're going to have 12 dots along here. If you count the dots, there's going to be 12. So there's one dot for each month. So let's have a look at another month. Let's have a look. I wanted us to focus on, here it is here, October. Look what happened in October. It was a bad month. The market was down 2.5% over here. And then stock A also had a bad month, not as bad, but still bad enough. It was down 2% for the month there. So this dot here in October, it's showing us a bad month for both the market and stock A. So what we can see is that when the market is doing badly, like these 4 months here are negative months, then stock A is also negative. But when the market is doing well, like in these months over here, where these dots are on this side here, positive months, then stock A is also performing nicely. So we can then see we've got this positive relationship between the return on the market and the return on stock A. And in order to get the scatter plot I did it in Excel. So what I did, this I had in Excel, so I just copied and pasted what was in Excel into the slide here. And then when you're in Excel and just highlight these 2 columns here, the numbers, you then go to, once you've highlighted, then you go to insert, and then you click on scatter, and then it brings up this nice scatter plot over here. Right, so now we can carry on in terms of looking at what is the simple linear regression all about. Well, all it is the estimation of a linear relationship between our dependent and independent variables. And this is now represented by a straight line. So this is the line that I drew in here. It's supposed to be a straight line. I didn't quite get it straight, but it's not too bad, eh? And we will see it perfectly straight later on. And why I actually drew it in before we started, because I was actually practicing just now to try and draw a straight line in and straight line in between these dots, and it was actually worse than it is here. So I thought, let me leave this one because this one wasn't too bad. Anyway, enough about that. let's get on with things. So what I want us to do is just focus on August again. So let's just recap. So in August, the market did 2.5% there, and stock A, it did 2% over there. Now, what we can see is that this straight line, or so-called straight line, this is our regression line. What is this straight line estimating that stock A is going to do if the return on the market is 2.5%? Well, all we need to do is go up to the up to the red line. So if the market has 2.5%, the red line is actually estimating that stock A is going to do 2.8%. So why do I say 2.8% with such confidence? Because we actually in a few minutes time going to see what the regression equation looks like for this example, and we're going to see that when we plug in 2.5% for the return on the market, the return on stock A, the estimated return on stock A, is actually going to be 2.8%. So the difference between this estimated return over here and the actual return over there, that is what we call the error term. So I'm going to put an E over there. That is the error term. And it's also called the residual. So I'll put /R. It's also called the residual. So this is a very important term, this error or residual. So I just wanted to talk a little bit about it now, because it's definitely going to help us if we talk about it now with what's coming up in the rest of this class. So then what this regression line is, and we will see it in words properly on the next slide. This regression line is actually the line that minimizes these error terms. It's the line that's in between the error terms. It's the line that minimizes the error terms. And some people call it the line of best fit. You may have heard that terminology before. But to be 100% correct, because that's the principle, but to be 100% correct, it's actually the line that minimizes the squared error terms. Now, why do we use squared error terms? Because it's almost like, think back to standard deviation and variance. We have to square these error terms, because if we don't square them, then the negatives would cancel out the positives, and negatives would cancel out the positives, and would have no error. So we will see on the next slide that it's the line that minimizes the squared error terms. So what is the error term? It is the difference between the actual value and then the estimated value according to the line. So what we will see, something like this, we'll see on the next slide, but I'll try and get it wording right, but it's something like this. It's the line that minimizes the squared distance between the actual Y value and the estimated Y value. So we will see it on the next slide, but now that wording but now that we've covered it here, when we get to the next slide, it's going to be nice and easy to understand. Right, so we just need to look at one more thing, and then we can move on from this. And that is that if we've got one independent variable like we've got here, we've only got one independent variable, which is the return on the market. This is what we call simple linear regression, and that's all we're going to be doing at level 1. But at level 2, what we're going to have is actually more than one independent variable, and that's what we call multiple regression. So as an example, for our return on stock A, there are many things, of course, that affect the return on stock A. Not just the return on the market will affect the return on stock A, but other things will also affect the return on stock A. For example, the economy. So we could use GDP as an independent variable. What else could we use? We could use consumer confidence as an independent variable. We could use inflation as an independent variable. So there are many things that influence the return on stock A. So if we have more than one independent variable there, that's what we call multiple regression. And we'll leave that for next year for level 2. We're just going to focus now on the simple linear regression. Right. So now this slide shouldn't be too bad because we've been through the hard work on the previous slide. So we've discussed this linear regression assumes a linear relationship between our dependent and independent variables. So this, I'm going to stop over here because where I'm stopping, this is the equation for a straight line if we think back to school. So the dependent variable we said is y, and the intercept we denote that b0. The slope coefficient we denote b1, and then the independent variable we discussed earlier, that is x. I'm going to leave this error term for now. We'll come back to it when we do our numbers example, because it's going to be not much easier then, but we already have an idea of what this error term is. So let's just continue then. We'll come back to that. So we cannot observe the population parameters values, bigger part, let me start again. We cannot observe the population parameter values B0 and B1 in our regression model because it is actually just too much information. So we can't actually get the population parameter values of our intercept there and our slope coefficient there. So what are we rather going to do? We're going to use estimates of them. So we're going to use, so when we've got a hat on top, let's call that a hat. Hat B0 is going to be the estimate of the intercept, and the hat on top of our slope coefficient, that is going to be an estimate of the slope coefficient. So now our estimated value for y, because it's got a hat on top, or we could say a predicted value for y if we prefer, all we're going to do is take our estimated intercept there, and we're going to add on our estimated slope coefficient there and multiply our estimated slope coefficient by our x value. And that's going to give us, once we've multiplied those two together and added on our intercept, that's going to give us our estimated value for y. An example is coming up in a few minutes. So here we go. Now, because we did all that hard work on the previous slide, we can actually go through this quite quickly. So in simple linear regression, the sum of the squared, that's what I was emphasizing just now, the sum of the squared vertical distances between the actual y values and the estimated y values, they are minimized. So if we just go back there just one last time, we're looking at the squared vertical distances between our actual y value there and our estimated y value there. So we're going to take these squared distances for each and every observation, right? Not just for this one, but for all of them. We take those squared vertical distances and then we sum them up, and we want to look, this line is going to be the one which minimizes those squared vertical distances, right? So we call these, when we sum up these squared vertical distances, we call this the sum of the squares errors. And the regression line, as we've been saying, is the line that minimizes the sum of the squares errors. And we are going to look at doing an example of some of the squares errors in the next class. So from this, we're going to get, from this line, we're going to get our estimated, like we've spoken about, we're going to get our estimated intercept and slope. And we call this our least squares regression, because we want the line that minimizes the error. So it's our least squares regression, or some people call it ordinary least squares regression. Good, fantastic. So now, how can we get this estimated slope coefficient? So there is a formula for it. I don't know how important it is for the exam, because, you know, the Excel or whatever can just work it out for us. But just in case, to work out the estimated slope coefficient, it's B1 with a hat on top. We can take the covariance here of y and x. So y is our dependent variable and x is our independent variable. So we take the covariance between them and we divide that by the variance of x, and x is our independent variable. So let's do it. So the covariance between the return on stock A and the market return, that is 3.13. So basically, how I got this, I didn't go and work out covariance. Remember what covariance? It shows how two variables move together. And it's that horrible long formula we did in another class. So I didn't go through that whole process to work out the covariance. What I did is, if we just go back here, I took the data here, and then all you do is in Excel, you go to formulas, and then you go to covariance, and then at first wants us to put in the independent variable. So you just highlight that column for independent variable. And then once you've done that, then it wants the information for the dependent variable, then you highlight that column. And then that is all. And then all you got to do is then click on the, you know, what you want covariance, you click on covariance, and that spits it out. So it was nice and easy. And then the same for the variance. So the variance of x over here, our independent variable is the market return. So to work out that variance, all I did is I went to formulas and I went to variance, and I highlighted then this. I want the variance of this lot, and it just spat it out for me. This was the variance. So remember that horrible formula for variance? We're going to look at, it's the sum of those squared differences between our actual values and the mean of x. But if you've forgotten how to work out variance, maybe just look at it just so that you understand what's going on. But it's not that serious. So anyway, so all now it's the easy part. So to work out the estimated slope coefficient here, we just take the covariance between the two and we divide it by the variance of the market return. And this is now our slope coefficient. So now I think what is most important is what is in this box here. What is this slope coefficient? It is the expected change in the dependent variable for a 1 unit change in our independent variable. So we're going to leave that for now because we're going to do an example on the next slide. Let's just have a quick look at how can we work out the estimated intercept. So the estimated intercept here, it's B0 with a hat on top. We can take y, that is y bar. Remember, we've got a little horizontal line over the letter. That is bar. So that's y bar. And what is y bar? It's just the mean of y, if we remember back. So we've got to take the mean of y, which is our dependent variable, and we've got to subtract then b1, which is our estimated slope coefficient, and we multiply that by x bar. So x bar is going to be the mean of x, which is the independent variable. So to work out the mean stock A return, so that is going to be the mean of our our dependent variable. It's so easy in Excel. So we know how to work out the mean of this column here. So this is our dependent variable over here. So we're just going to highlight this lot over there. And then all I did is I clicked on average and it worked out the mean. So that we got the mean then of stock A, or of the Y variable, the dependent variable. The mean of Y was, there it is, 0.81. That is our stock A. And then we need to do the same for what's the mean of the market return there, X bar. So for this one, we would just highlight this column here, and that would work out what is the mean of the market return, and just click on average, and it will give us there. So we can see the mean of stock A was 0.81% over the year. The monthly return was 0.81%. The mean monthly return was 0.81% for stock A, and the mean monthly return for the market was 0.45%. So now all we need to do is plug in the numbers. So to work out the estimated intercept, all we've got to do is take the mean of the dependent variable, which is 0.81, and subtract the slope coefficient there, which is 0.97, and multiply that by the mean here of our independent variable, which is the mean market return, which was the 0.45. So there we get our estimated intercept. Now, again, I think this is the most important part. What is the interpretation of the intercept? So the intercept, it is the expected value of our dependent variable when the independent variable has a value of 0. So again, we're going to leave that for now because we're going to see it on the next slide. But now we're in a position to draw up what is our regression model equation. So the estimated or the predicted value of y, that is going to be our intercept there, the 0.37, plus our slope coefficient there, the 0.9704, and we multiply that by the independent variable, whatever the value for the independent variable is. We plug that in, and then that is going to give us an estimated value for our dependent variable. So let's give it a go. Let's give the example a try. So now on this slide, we've got the regression line drawn in properly this time. It's not my scroll or my attempt at a straight line. So what I did over here in Excel is, when I was in Excel, you can right click on any one of these dots, and then you go to so once you've right clicked, you go to trend line, and the trend, once you click on trend line, automatically this regression line comes up like a straight line. And remember what it is the line that minimizes these error terms, right? So that's what we've got as we've discussed. So we saw on the previous slide that the slope was positive 0.97. So what does that mean? Remember, this slope, what it is saying, if we think back to the previous slide, the slope was saying it's the change in the dependent variable for a 1 unit change in the independent variable. So our market return is the independent variable. So if the market return goes up 1%, this means that the dependent variable is going to change by what the slope is. So the slope is 0.97. So if the market return goes up 1%, then stock A return is going to go up 0.97%. So because we've got this positive relationship between the two. Okay, so if we had a minus over here, what would the situation then be? If we had a minus over here, then when the market return went up 1%, then stock A return would do what? It would go down 0.97%. But we have a positive relationship. So when the market's going up, stock A is going up. And then this also will make a lot of sense to you. I won't have to read this one to you. You can figure that one out. Okay, so now, we've done the slope. And then what about the intercept? So the intercept, we worked out is 0.37%. That is over here. So there's the intercept there. That is 0.37%. So what is that saying? So remember, the intercept is saying when the return on the market over here is 0%, when the return on the market is 0%, then the expected return on stock A is going to be 0.37%. So that is going to be over there, 0.37%. So here is our regression model equation that we did on the previous slide. So now comes August. So remember August that we did on our first slide, and as promised, here it comes. So if the return on the market is 2.5%, what is our model going to predict? The model predicts the return on stock A is going to be what? All we need to do is plug in 2.5%, because remember this over here is our X here, our independent variable. So if they tell us it's 2.5%, we just got to plug in 2.5% for our X, and then we see what the predicted value is, or the estimated value according to our model. It's 2.8%. So over here is our 2.5% there. If we go up to the line there and to the left, we are predicting the 2.8%. Right, that's why I said it with so much confidence a few minutes ago, the 2.8%. But here comes the but. As we know, but when the return on the market is 2.5%, the actual return on stock A, it was 2%, that was August. Remember our friend August? So when the market did 2.5%, the actual return on stock A was 2%. So this difference then, the difference between our actual return of 2% and our estimated return of 2.8%, that is our residual there. That is our residual, the difference between the two. So it's minus 0.8%, or it's called our error term, like I mentioned earlier. I think I called it error first / residual. So that is what the difference between the actual return and the estimated return is. So our actual return, remember this formula, the actual return, if we go back as promised, we said we would, this is the actual return. There's no hat now on Y. So the actual return of Y, we're going to take our estimated return, and then we're going to take into account the error term to work out our actual return. So let's do that. So this part over here is our regression equation, and this is our error term. That's going to give us the actual return. So let's do it quickly. Where are we now? Over here. So to work out the actual return, then we take our regression equation and then we account for the error there. So here's our regression equation there. So this, what I've underlined, that was the 2.8%. So let's just write in 2.8 over there like that. So we take our 2.8% from our regression equation over there. And then if we take off, now we got to subtract our error term, because the error term was negative. The actual return was 2%, because there is our estimated return there, hey, the 2.8%. If we subtract the error term, the 0.8%, that's going to give us what the actual return was. Okay, so all should be nice and clear now that we've put the numbers to it. Fantastic. Right, so now the last thing we need to look at in this class are the assumptions underlying the simple regression model. And there are 4 that we need to know. And the first one we've discussed, linearity. So we've assumed, and we said this from the start, that there's a linear relationship between our dependent and independent variables. So if we have a non-linear relationship, that's a problem. Then we can't actually do linear regression. So over here is a situation of a non-linear relationship. Now, just before we look at the scatter plot, I just want to read the LOS to you, because I got it handy. I've kept it handy. The LOS says, explain the assumptions underlying the simple linear regression model. Okay, so there's the 4 assumptions we're going to know. And now here comes the other part, and describe how residuals and residual plots like this, residual plots, indicate if these assumptions have been violated. So we need to be able to tell from these residual plots if these assumptions have been violated. So what we can see from this, remember what the residual is, like we spoke about on the previous slide. It's the actual value, which is the blue dot, less the predicted value according to our regression line, the straight line. So what we can see here is that the residuals, they're positive when X, when the independent variable here has got low value, because when the independent variable has got low values, then the actual values are above the predicted values. So the actual values are greater than the predicted values. So this means that the residuals will be positive because we've got a bigger number here, subtracting a smaller number on the line. But when the X becomes big, when the independent variable becomes a bigger number here, then the residuals become negative numbers because the actual value now is be less than the predicted value. The actual value is less than the predicted value. So then we're going to get negative numbers. So the residuals will be negative when X has got high values. In other words, the residuals, they are not random. They are positive here when X is small, and then negative here when X is big. So if this is the case, then we have a non-linear relationship, and we cannot use the linear regression model. So if we go back to our example, we're going to see the residuals. These were random because the residuals, some were positive and some were negative, some positive there, negative there, positive, negative. So that they are, more random. So this we can see is working in terms of a linear relationship. This one's not. The actual relationship's like this. It's up and then down and up. So it's not linear. It's not these things are not going in a straight line, these dots. So this we could not use. Okay, so then the second assumption is this funny word, homoscedasticity. So that means the variance of the residual terms, are they're the same for all observations. Now remember what variance is. Variance is just volatility. And we're talking about now the volatility of these residual terms, the actual values less the predicted values. So we're talking about how spread out are these residual terms around the predicted values. So we can see that when the independent variable here, the X, when the independent variable is low, when it is small over here, then the residuals, they're quite close. The residuals are low. The difference between the actual value and the predicted value is low. So we've got low variances. The residuals are not spread out. But when X is high, when X becomes bigger, then what do we see? We see the residual variance is high. The difference, the volatility, or how spread out are these residuals compared to our line, they're very spread out over here. So this means that the variance of the residual terms, they're not the same. So if they're not the same, we have a problem. And that problem is another funny word, is called heteroscedasticity. So if we've got heteroscedasticity like over here, we have a problem. And then the assumption is being violated, and we cannot use the simple linear regression model if our data is like this, right? And then the third assumption is independence. So what we need is that our observations, our Y and X pairs that we looked at on our first slide, these guys here, let's just go back there quickly. These guys over here, these Y and X pairs over here, these guys, we not? Okay, these guys, they must be uncorrelated with one another. So if they are uncorrelated, they are independent, all is good. But here comes the but. If there is correlation between them, we call that autocorrelation, then they are not independent. And if they are not independent, then we have a problem, because the residuals, they will be correlated. Because for independence, the residual terms, they actually must be uncorrelated. So let's have a look at this example over here. So here we've got the quarterly revenue of company A regressed over 12 quarters, in other words, over 3 years. So what we can see is that we've got the revenue here along the Y or the vertical axis, and we've got the quarters along is our independent variable or along the horizontal axis. So we can see what we've got over here is that the revenues, they display a seasonal pattern. So have a look here. So this is quarter 1 of the first year, then quarter 2, then quarter 3 of the first year. Now this is quarter 4 of year 1. So we can see that quarter 4, the revenue spikes up tremendously. So, and then it drops down again. This quarter 5 is going to be the first quarter of year 2. And that's going to be the second quarter of year 2, the third quarter of year 2, and this is now going to be the fourth quarter of year 2. So you see what happens in the fourth quarter of year 2, again, the revenue spikes. So this, let's say this is a toy shop, for example. And when do toy shops sell most of their toys? Of course, over in the fourth quarter, over the Christmas period. So that's why this revenue is spiking like this, and then it drops down immediately in the first quarter of the next year. It drops down again. So this dot over here will be the fourth quarter of year 3, and again the revenue is spiking up tremendously. So the revenues, they display what we call a seasonal pattern. They jump tremendously in the fourth quarter of each year. So the residuals here, the difference between the actual value and the predicted value, they are correlated because they spike in the fourth quarter of each year, and then they fall back in the first quarter of the following year. Right, so that is a problem. And if we've got this problem, then we cannot use our simple linear regression model. Right, and then lastly, the last assumption is that of normality. And what we mean by this is that the residual terms, they must be normally distributed. Now, we don't have to go into all the detail, thank goodness. We just need to know that the residual terms, they must be normally distributed. And I just put a note in here that our dependent and our independent variable, and our dependent and independent variables, they don't have to be normally distributed. Just the residual terms must be. And I saw one of the CFA Institute practice problems that was trying to trick us, where they said, you know, one of the assumptions is that the dependent and the independent variables must be normally distributed. No, that is not a correct answer choice. They don't have to be. What must be normally distributed? The residual terms. Good. So that is then the end of that class. I hope it was helpful, and we'll see you guys in the next class. Hello, it's Tim here again. I hope you enjoyed the class and found it beneficial. We have some classes available for free on YouTube, but we have classes for the entire curriculum. The classes that are not on YouTube can be purchased from us. If you'd like to purchase the classes, please contact us for the pricing, and I've put our contact details over here. You can purchase all the classes or certain readings that you would like. When you purchase the classes, we provide you with the slides and our notes. I've assisted hundreds of candidates pass CFA exams, and I look forward to also helping you through the CFA program. I've put in 2 testimonials in the slide over here, and we also have a testimonials page on our website that you can review. I look forward to seeing you soon, and all the best.